Hello, ENET 140 op-amps class. We are back for the third and final recorded lecture regarding basic op-amp circuits from our Fiori textbook, Chapter 4. Excuse me. When we left off, we had finished the basic concepts of idealized op-amps with negative feedback. And just to recap, that is infinite input impedance into both the inverting and non-inverting terminals. And then second, and probably more useful, is equal potential at both of those terminals. So that's what allowed us in the case of the grounded non-inverting terminal with an inverting amplifier to allow us to have that virtual ground up at the inverting amplifier input. And that made it very easy to simplify circuits and calculate gain. So we're going to build on the basics that we walked through with the inverting voltage amplifier, the non-inverting voltage amplifier, and then our transducers, our voltage to current amplifier and current to voltage. And we're going to look at kind of an expansion now of the inverting voltage amplifier, and say what happens if we put not one but multiple voltage signals in. And a thing to remember when we're talking about voltage signals, we're not talking about just increasing voltage, like say for power purposes. These voltage signals are information signals. They're coming from an instrument or something, so you want to retain their specific frequency, phase, other characteristics that carry the information. So when we talk about summing them, we want to know how we would add these signals with respect to their total amplitude, phase, frequency relationships. Everything like that has to be retained. And that's one of the reasons we use these types of circuits. That is a little bit beyond the scope of this chapter, but I just wanted to get it into your head just to make sure we're not talking about what could be accomplished with, say, a step-up transformer, because that also can increase voltage, but wouldn't necessarily maintain the signal characteristics that would allow us to get information out of it on the output. Okay, so this is the basic configuration of the summing amplifier, inverting. So we have 1, 2, 3 in this case voltage signals coming into the inverting terminal. So we suspect that if these are all coming in as positive, we're likely to have a negative V out. We'll see, but we would suspect that. And they each have a different resistor. They each have a different amplitude voltage signal. And so, not surprisingly, they'll have a different current flowing through their input circuits here. So we have these all labeled I1, I2, and I3, just like we would do analyzing any DC circuit. So not surprisingly, all of those currents are going to combine at VA. So by Kirchhoff's current law, we know that if we have I1, I2, and I3 flowing into VA, the I out that we have flowing out of the VA node point is going to have to be the sum of those currents. So we can say that first off, I out is the sum of, and this is a summation, mathematical summation symbol. It's a little bit easier to write than I1 plus I2 plus I3, but this says the sum of I sub anything, and all of the anythings is equal to I out. So summation symbol. And so again, this is just Kirchhoff's current law. Okay, so let's look from the Kirchhoff's voltage law standpoint. If we take any point here, V1, so we got an input voltage signal coming in. We have selected R1, or somebody selected it for us, maybe a colleague built the circuit. So we know that I1 is going to be V1 minus VA divided by R1. We can apply Ohm's law and relate this voltage to the input voltage to the resistor. So we can write an expression for the voltage at any one of our inputs in terms of the voltage drop over their input resistors. So we can say V sub x, which is like V sub 1 or V sub 2 or V sub 3, minus R sub x, so that's the resistor that goes with that voltage input, times the current flowing over that resistor, equals the node voltage. So we just KVL'd each one of these branches to this node. Okay, so now we can express input voltage, input resistors. We got a current that we would have to measure, but we don't want to, and our node voltage. Well, what we eventually are going to want is V in our Vx's with respect to the V out. So let's proceed down the circuit and get an expression for V out in terms of things that we know. If we do the same Ohm's law, from VA to V out, we can say that the voltage at A minus the current that flows through the resistor, it's just real basic Ohm's law again, is going to equal the voltage at this point, which is V out. So V sub A minus I out times R sub F equals V out. Well, I out is just the sum of all of those currents, and that's all of them. So you get a lot more current flowing through RF than you do any one of these input resistors. But that's okay, we can sum them up. Or we can write an expression for them. So we can say V at node A minus the feedback resistor times I out, which is the sum of all the I ins, equals V out. Okay, so now we have two equations, three equations when we count Kirchhoff's current law, and, well, more than three. We have one of these for every input. So that ought to be enough to rearrange and get an expression for V out in terms of V in and our feedback and input resistors. So we know what we're looking for in terms of the gain on any one of these individual voltage inputs is V out divided by V in for that input. Well, we can write V out as just the feedback resistor times the output current. Hey, where did V sub A go? Oh, that's a virtual ground. Our non-inverting terminal is a ground, so V sub A is 0. So I out is just negative RF, or excuse me, V out is just negative RF times I out. So that's what we have in the numerator here. V in, likewise, great. This is 0. We take R sub x, I sub x to the other side, and we have an expression for the input independent of any voltage here at VA because it's 0. So we have negative RF times the total current output, which is the sum of the inputs, divided by any one of the input resistors, the resistor for whose branch we're looking for the gain, divided by its current. And so we can express gain on any branch as the ratio of negative RF over RX, which is exactly like what we saw with the inverting, the one input inverting voltage amplifier, sorry about that, times the ratio of the currents. So we can apply that down here if we want with an example. So this is Fiori example 413. And we're going to see that those sums of the currents are going to have a relationship to the voltage as well, especially if those input resistors are equal. That might be an exercise for later. Okay, so our example, we have a 1 volt input voltage signal, a -2 and a 0.5 positive. So these are all DC signals. We have a 4 kilo ohm resistor, a 2 kilo ohm resistor, and a 1 kilo ohm resistor on the input, and then a 10 kilo ohm feedback resistor. Somebody wants to know what the output voltage is. Okay, well, we can go through the same steps that we used to derive this and say that the output voltage can be written in terms of VA, which is virtual ground, as just minus your feedback resistor times the current flowing through it. So 0 minus whatever current is flowing through 10K equals V out. We can write expressions for the currents flowing through each of these branches, just using Ohm's law. So current flowing through the 1 volt branch is just 1 volt divided by 4 kilo ohms. It's 2.5 times 10 to the minus 4 amps. We do the same thing for each of the other branches. Add up all of these numbers, and we get an I total of negative 2.5 times 10 to the minus 4 amps. So that's actually flowing the other way. So conventional current would be flowing net in this direction, and then it would branch. Okay, no problem. We can deal with negative numbers. So now that we have an I total, we plug it in and we get the output voltage as negative 2.5 volts. So it's a combination at the end of the day of the input signals and their respective resistors. It ends up being a sum if all of the resistors are equal. Just to note that since these were DC signals, had they been AC, we would have had to use our complex addition. We would have had to put them in rectangular coordinates and add up our real and imaginary components. And then we would have gotten an output signal that had, instead of just a positive negative, it would have had an amplitude and a phase angle with respect to all of the inputs. But that's no big deal. We can add things up and divide things as complex numbers, no problem. And that's the general procedure we do. Okay. It gets a little trickier when we want non-inverting because we have to do a little bit more math to figure out the potential and the currents at this point. So here's our general schematic of our summing amplifier non-inverting. So here's our input signals, V1, V2, V3, each with their own respective input resistor, R1, R2, and R3. Here's our non-inverting voltage point, which is labeled at VA again. And we have a feedback network on the inverting terminal, of course, because we want negative feedback, right? Notice in all of these cases we may have a lot of resistor networks on the non-inverting terminal, but our feedback loop, remember, always has to be back to the inverting or it wouldn't be negative feedback. And the last amplifier we'll deal with is what we call a differential amplifier that has summing and some amount of feedback on both, but will have a net negative feedback, and that'll always be through your inverting terminal. Okay, so let's march through this and see how this compares to the inverting summing amplifier. Well, the first thing we can say is our feedback voltage point here, which is the input to the inverting terminal, VF, and we'll call it VF because that's has the potential of V feedback by dint of the feedback fraction flowing through our resistor here. We defined that terminology back in chapter 3. We know that's going to be equal to V sub A because these two terminals have to have the same potential via our idealized assumptions. So V sub F equals V sub A. To get V out, now we've got to somehow relate V sub A to all of these. If we knew what V sub A was, we could just deal with this as a standard non-inverting voltage amplifier. But this V sub A is going to have a relationship to our input, hopefully anyway, because we're going to do something with it. And then that will in turn affect V sub F. And then we can say something about the way currents flow, which will give us our V out. So let's think about that again. V out is going to be controlled by the properties of the amplifier and the voltage at our non-inverting terminal, which itself is going to be a function of our inputs. This voltage set by the inputs is going to reflect down to V sub F. It'll be a known quantity that we can calculate based on combining these somehow with simple rules of DC circuits or AC circuits. Once we know this voltage, we can say something about currents through these two resistors, and we should be able to say something about the output voltage. So that's how we'll relate input signals through V sub A down to V sub F, use some KVLs and KCLs, relate to the output. Have to walk from one end of the circuit to the other to get what we want. Okay, so the key to all of this is what's V sub A in terms of all of these different voltage inputs and their resistors. So it's really just an AC or DC basic circuit analysis to get the voltage at this point. Well, the first thing we do is we remember that no current is flowing through V sub A. or excuse me, V sub A, through point A, node A. No current flows into the non-inverting terminal in the op amp. We can use our other assumption. So we can redraw the circuit like this, and we can assume that all of these voltages are, let's say right now, that they're DC sources referenced to ground, because they're referenced to ground somewhere. So let's redraw them as all referenced to ground. So you have voltage source 1, again we're assuming is DC. It's going to cause a current 1 flowing through R1, and we've just shorted across all the resistors. We want to know what the voltage point is anywhere along this short. We have 3 voltage sources and 3 resistors and 3 currents going each through their own separate branches. Wow. I don't know about you all, but it's been a little while since DC, so I decided to use 2 different methods to solve this. One that I admittedly had to look up that I thought was more elegant than the one I started with, which still got me there. So I'm going to show you both. And one of them is sort of a brute force method, which would get you there anywhere, regardless, and is very amenable to very, very large complex circuits, and that's a matrix method. And it relies directly on KVLing and KCLing each of these branches, or KVLing each branch and then KCLing the node point. So I'm going to apply Kirchhoff's voltage law to each of these branches and express the voltage at point A in terms of ground and voltage sources and voltage drops over the resistors. Then I'm going to sum all the currents at A using Kirchhoff's current law. So I'm going to start with, let's start with branch 3. So I go from ground and I go up in voltage over my voltage source 3, and that's my input signal 3. I'm going to subtract I3, whatever current is flowing over resistor 3, and that's going to give me V sub A. And so that's equation 1 here. I can do a similar KVL for each one of the other branches, and I generate 3 independent equations. And it's independent because neither one of these rely on each other. So I have 3 equations now, and I have 1 unknown, 2 unknown, 3 unknowns, 4 unknowns. VA is what I want, and I don't know it. I also don't know the currents going through these branches, I2, I3, or I1. I can, if I wanted to solve this algebraically, I have 3 equations and 4 unknowns, so I don't have enough equations to solve it with math. So now I can quick draw Kirchhoff's current law applied to point A, and that gives me a 4th equation. So I can say that the current 1 plus current 2 plus current 3 equals 0. They all come into A, but remember, because A is an isolated node, effectively, infinite input impedance here into the op amp, these 3 currents have to sum to 0. So if I1 is bigger, one of them has to be flowing backwards, in other words, effectively, because nothing can flow out of A into the op amp. Okay, so there's my equation 4. That's what these EQs mean if you're reading the notes. So equation 1, equation 2, equation 3, equation 4. And then my unknowns are my voltage at node A, which I really want because that's what's going to give me the gain in the op amp, and then my 3 currents in each one of the 3 branches. So if you're taking pre-calc or linear algebra or heading into any kind of math class, you'll know that there's a lot of different ways that you can solve linear equations. Any number of variables, if you have the same number of equations as unknowns, you can solve it, and you can get values for all of these. So I'm going to walk through a method, and this is a little bit beyond the scope of just this chapter, and you will not see this on the exam. So if you want to fast forward through this part of the recorded lecture, you will not be questioned on it on the exam, but if you're going to go into this field, and certainly if you're heading into engineering, this is a really handy trick to set up. Even if you're at the technician level, if you're analyzing or designing complex circuits, this type of analysis is really, really useful, and some calculators even have matrix manipulation on them. So this is something that you could actually do like in your truck out in the field if you had to, if you wanted to design a circuit. Okay, it's called a matrix solution of linear equations. So the way we do this is we write each one of these 4 equations such that each one of the variables has its own column. So I just rewrite them. I get all of each of the unknowns in their own column. So this was equation 3. I rewrote by pulling v sub a over to this side, and then I had a column for I1, I2, I3, and then the v sub 3 came over to the other side because it's a known and it's a constant, not an unknown. So I have unknown 1, v sub a. I have 0, I1, flowing through current branch 3, so I just put a 0 there, a 0 coefficient for I2, and then I have R3 multiplied by I3. So that's just a rewrite of this equation. Excuse me, I do the same for equation 2 and equation 3, and then I rewrite my Kirchhoff's current law the same way. I have no v sub a's in equation 4, it just isn't there, so I put a 0. And then I have 1 I1, 1 I2, 1 I3, and that all summed to 0. So it's just a rewrite of the 4 equations to get each of the unknowns all in their own columns. Okay. If you use properties of linear equations in matrices, you would know that if you took this matrix, which is just the coefficients of all of the terms on this side, and you multiplied this matrix by a column matrix of all of our unknowns in this arrangement, you could replicate everything on this side. So for anyone who's in pre-calc or who will get to matrix multiplication, everything on the left-hand side of these sets of equations, if I made a matrix out of all of this, it would be the product of this matrix times that matrix. This is just matrix multiplication. And then I turned all of these constants into just a vector matrix on this side. Now, a property of matrix multiplication that's just like algebraic manipulation is that if I multiply each of sides of this equation, because this is just a big equation with matrices now, I have this matrix times that matrix equals that matrix. This is just another way of expressing these linear equations. Just another way. If I had something like 2a times 4 equals 10, and I wanted to take the a to the other side, I would multiply by the inverse of a, or 1 over a, and it would move it. I can move matrices by multiplying by their inverse the same way. And in fact, an inverse matrix is whatever matrix you have to multiply one matrix by to get what is effectively a 1 matrix, the unit matrix. So if I multiply this side of the equation by the inverse of this matrix, and then I multiply this side of the equation by the inverse of this matrix, do to the same one side which you do to the other, rules of equations, I'll get my solutions, or I'll get all of my unknowns equaling a matrix that just has numbers. So I will get actually the solution to them. So that's just a quick way, if you have a calculator that multiplies matrices and does matrix inversion, which again most do, and Excel will do this if you're interested, you can solve all of these and get your V sub A and get all your currents. But most importantly, you'll get your V sub A. And if you've got maybe 10 of these, while you can go through a simpler algebraic method, which you will be tested on, which I'm going to show you in a minute, if you end up having a lot of these, the matrix method really is the best way to go, maybe the only way to go to get the solution. So now you've heard of it, and I worked through it, by the way. It was great. I put in the same numbers that I did over here for an example, and it worked beautifully. Anyone who's interested in learning to do that, let me know. And if you end up taking linear algebra or pre-calc later on, this is a great place to use it, or for a project or something you might be interested in. Okay, so back to a better method for doing a smaller number of these. So again, we're still just trying to get the voltage at that point A. It's the result of all of our inputs. So if we just do some direct substitution into our Kirchhoff's current law expression, so we do our I1 plus I2 plus I3, We can write any one of those currents in terms of the voltages. So we can apply Ohm's law individually to each one. So I1 is V1 minus VA over R1. Right, that's just back here. I1 going through here is VA minus V1 divided by R1. And so we write that for each one of our currents, add them up, because we added up the currents, we add up the current equivalent expressions, and you'll notice we've got one equation with only one unknown there. So if we distribute R's, do some algebraic simplification, we can get a single expression that has just our R's and our V's and get our voltage at point A. You will notice if all the R's are the same, we end up being able to relate our input voltages a little bit better, and we do get the sum of them. We can factor out our 3R. So I'll leave some math to you to try that. But if you have different values of resistors and voltages, you can still use this expression that we derived just from Kirchhoff's current law and Ohm's law in each case to get V sub A. So once we have V sub A, we're right back to what we did with classic non-inverting op amps. So we can say V sub A coming in here, we can rewrite and get rid of that whole sum because everything in that sum is now contained within V sub A. And we can direct that to the non-inverting terminal. We can say it's equal to V sub F and go through our algebra. Using RF and RI as a voltage divider and knowing that V sub A is really, at the divider point, and get an expression for gain. So our voltage ratio gain for our node here is simply 1 plus R sub F over R sub I, which we saw right at the very beginning. And again, remember that is in terms of our sum point, our V sub A node. Okay. And I am not going to go over the cases where the resistors are equal, where you can actually see the summation. We'll leave that for maybe an exam question or a homework question. But now you know the steps that you would go through to get gain regardless. So you can walk back through those steps and apply it to any circuit. Okay, the last individual type of amplifier that we're going to go over is the differential amplifier. This really should sound familiar because we went through the discrete components that could make up a differential amplifier right at the beginning of the course in chapter 1. So we actually made a differential amplifier out of a series of BJTs and biasing resistors. And then we went on to say that every op-amp, every operational amplifier, regardless of the package that it had or its performance characteristics, usually had a differential amplifier stage or section for its front end. You'll also notice when we're manipulating op-amps, there's always two input signals. Even if one is grounded, when we're using the other, we have effectively a voltage difference or a current difference going into both terminals. And that's because the first thing that you hit inside this hypothetical triangle of circuitry is usually a differential amplifier circuit. So we're going to take advantage of the fact that all op-amps are effectively diff amps, and we're going to look at putting in a little bit more complicated signal into both the inverting and non-inverting terminals and see what we get. So we kind of have something that looks a lot like a voltage divider, looks like a feedback network here in both cases, but it is only R2 up here that is actually accomplishing the feedback because it's the only one that is connecting the output voltage back into the inverting terminal. So R2 is our feedback resistor, R1 is serving as our inverting terminal input resistor, and these are just adjusting our voltage going into our non-inverting terminal. So now we have two voltages input coming from ground. They could be AC or DC, but we're going to reference them both to ground. And we can do KVL And KCL on both of these, we know that V sub A equals V sub B. We know that the currents flowing into these input nodes sure don't flow into the op amp. So we can KVL from ground to ground and get some expressions for voltage at the output relative to the input. So this is basically the same thing we did for the inverting and non-inverting, except we're going to do it for both at the same time and come up with one big expression for input voltages and resistors. So we can just step through that. At this point you guys should all be able to do this, but we'll just step through this real quick. So I can write an expression for I1 in terms of V sub A, which is going to be the same as V sub B, but I'm going to have to carry it along because it's not a virtual ground now. Notice that. Ground is down here, and my non-inverting terminal is above ground by whatever I2 times R4 is. So we can't turn it into a 0, but we can turn it into a known number. It's almost as good. So V sub I is going to be V1 minus VA divided by R1, Ohm's law. And that is going to be the same as V sub A minus V out divided by R2, because I1 flows through here too. So this is like saying I1 is equal to I1. So this is in series path. No current flows in here. So it goes from here through the feedback resistor into V out. So I can write a similar KVL expression for V2. I go up from ground to V2. I have I2 flowing over R3 and R4 back to ground. So I can write an expression for part way and all the way again. So I can write this part of the KVL, V2 minus V sub B divided by R3 equals I2. And that same I2 flows through here. So I can say V2 minus ground divided by the series resistor is also going to be I2. So voltage divider. So now I have these two expressions, and I'm going to simplify them a little bit, isolate the V sub A's and the inputs. So I've distributed R sub I to V1 and VA, distributed R2 to VA and V out. So now I've got 4 individual fractions. I'm going to throw V out all by itself on one side. Got the other terms on this side. Then I'm going to multiply R2 back over to all of these terms, collect them together, get all the VAs in their own term and the VIs on their term. And I end up with V out all by itself, and then R1 plus R2 over R1 multiplying V sub A, and R2 over R1 multiplying V sub 1. So I've got my V out expression. There's equation 1. I'm going to do the same thing over here, just do some algebraic wrangling, and I'm going to get V sub B on all by itself. I won't talk through all the steps, you can just see what I did. Just basic algebraic manipulation, distributive property, factoring, moving things around in an equation, but I end up with V sub B. Now since V sub A and V sub B equal one another, I can take this whole expression and plop it in right over here for V sub A. And when I do that, and I do a little bit more simplifying, I end up with this expression relating all of my R's and my 2 input signals to my output signal. So the R's are things that you'll design in a circuit. Your feedback resistor, your inverting terminal input, the voltage divider for your non-inverting signal. You're going to presumably know what your input signals are, and this tells you what you expect for your output based on your inputs. Let's see if some things make sense. Let's see, we've got a negative sign in front of the terms associated with V1 and the resistors. Well, that makes some sense because it's going into the inverting terminal. And we have a positive sign related to V2 and things associated with its resistor, but it's got some relationship to the resistor network on the inverting terminal as well. And that's because, again, these two node points talk. So that does make some sense as a sanity check. So your output signal is dependent on everything to do with your input. Okay, adder subtractor. We can take this same concept that we just did with the diff amp and the two concepts we did with the summers at the inverting and non-inverting terminals and combine all of them together. So we would use all of our algebra and combinations of equations to get our voltage points at A and B, and then use those same the same procedures we used back here with the differential amplifier to get our output. So it's basically an all of the above. Excuse me. So if you walk through all of that math, which you will not be required to do for this class, you will end up with this universal expression for your output in terms of the sum of all of your inverting terminal voltage input signals minus the sum of all of your, this is your non-inverting voltage input signals minus the sum of all of your inverting. So it is actually the sum of all the ins going to the non-inverting minus the sum of all the ins going to the inverting. So it's a sum and then the difference of the sums. So that's a big derivation, and that assumes, it's another big assumption here, all the resistors are the same. So this is actually a pretty simple expression. It's just the sum and the difference. We don't have all of those 1 over r's that we had back up here. That's because they're all the same, and they all ended up combining and canceling out. So quite often when we're working with these summers and adders and subtractors, you'll work with resistances on the input voltage signals that are the same, so that you can get this summation relationship. But you can still calculate the output voltage and the gains even if the input resistances are different, and we just proved that you can. So almost done. Just a word here. Now we're done with the big equations, and we're just going to give a word or two to general design. So far we've been working with, we haven't even been showing our supply voltages. We did a lot of that with comparators because we were slamming from rail to rail because we were open loop. We didn't have a feedback network. So once we put our feedback network on, the only time we even thought about supply voltage was when we had a large value, large ohm load resistor, and we were putting a lot of current out, especially with our voltage to current converters, and we wanted to make sure that we weren't asking the output to give us a higher voltage to ground than the supply. So we just kind of use this as a check of clipping. So we're going to look a little bit more at using different types of schemes for supply voltages, and the circuit that you see here is what's called a one-sided or a single supply biasing. And it makes a lot of sense because if you think about it, going from say 30 volts here at Vs plus to ground is the same in terms of net supply difference as going from maybe a negative 15 to a positive 15. So some op amps are designed to be supplied from one side, so you can hook the appropriate terminal to ground instead of having to have a split supply. Of course, if you need a split supply, we all know how to use a voltage divider to get one. We just wanted to go over the fact that these do exist, and if you're hooking it up, please refer to your spec sheet. Some are designed to work in single side supply, some op amps are and some are not. A few other words about this is a more realistic circuit. It has coupling capacitors. So our textbook author put this in under single side supply and then actually spent more time talking about the coupling capacitors. And I think that's just to get everybody remembering that in a real life op amp, we don't want our DC supply signals that we might be using for biasing, for adjusting our AC input to be in the proper portion of our amplification circuits. Remember all of those biasing and staying in the middle of your BJT's functional range that we did in semiconductors, those apply to certain portions of the circuit within the op-amp, especially the push-pull class A and class B and AB sections where we're actually amplifying immediately prior to the output. So this shows an op-amp in that same situation where we have a coupling capacitor on the input, so we don't have any DC offsets coming in that we didn't want, and that we're also not interfering necessarily with our supply and our AC input. And we have the same thing here on a feedback network. If there was some AC signal coming out, which since it's our input we hope there is, it's going to be effectively decoupled from any kind of DC signals coming in from ground. So because we have these coupling capacitors here now at these three positions, all of the performance of the circuit, even though it has negative feedback, is going to be frequency dependent. So that is something we started with in Chapter 1. So here is your leading frequency dependence characteristics, where you have a signal coming in and you have a leading capacitor, and now here's your capacitor that's resulting in lagging. So I'm not going to go into the math here, and Fiore doesn't either, but this is just an awareness that when you run op-amp circuits for real, and you did include these capacitors in a couple of your labs, you're going to introduce some frequency dependence, even when you have negative feedback and you have expanded the mid-band range. So remember, that was a big assumption we made at the beginning of Chapter 4, is that we were working in the mid-band, and we weren't going to sweat frequency dependence. We would assume that there wasn't any. In real life, when we put in our coupling capacitors so we can have offset only when we want it, we reintroduce a greater level of frequency dependence. And characterizing that is totally beyond the scope, at least of this section, in this portion of the course. Okay, a word about current boosting, and I did mention it in reference to, and I'm pointing to the front end or the back end of the op-amp because it's usually the third stage. Current boosting. Most op-amps are limited, most general purpose op-amps are limited to about 20 milliamps output. There's no saying you can't put this op-amp in a cascade with other amplifiers that will give you current boosting. And if you go back to your semiconductor studies and you remember our classes of amplifiers, we had an A and an AB, and a B and a C and a D for pulse mode, excuse me, my tongue is getting tied here at the end of the lecture. Pulsed mode modulation, which is more like what we get as a comparator. In any case, you can put especially the Class B and AB type of single stage amplifiers after your op-amp to get the current boosting you need, if you need more than the 20 milliamps that a single op-amp is likely to supply. So just be aware of the functional limits of the circuit. And this is very likely, by the way, one of the reasons why our classroom function generators that are so limited in their current output, they very likely are relying on not a lot of post-amplification, signal amplification boosting. Maybe they just have a single 20 milliamp op-amp and a single booster stage after that. If you wanted to get 1, 5, 10 amps or something out of that, you would have to have a cascade of current boosting coming after your voltage signal boosting, and then design it such that you didn't interfere with the fidelity of the voltage signal that you just worked so hard to preserve here. Okay, that is it. Definitely all of these last concepts with single supply biasing, don't dive too deep into this. If you read the textbook, it's very qualitative. Just be aware that you can supply some op-amps with one side. Remember, you can always use a voltage divider to do a two-side supply if you need it. Just build a voltage divider and supply from both sides, taking off different points in your divider array. And be aware that most op-amps are going to be current limited. And again, you'll see the 20 milliamps max output on quite a few devices. Not to say there aren't some that give more, and certainly there's probably some that give less. So back to read the spec sheet. So that is it for basic op-amp circuits, Fiori chapter 4. You should have a quiz out on Canvas on this material, and I will be posting some example problems from the end of the book. I'll be doing the odd problems so I can check myself too, but you can look at how I worked through them, and we will have an exam later on this material. This will probably be its own standalone exam because it was such a long chapter and there's so much material in it. And then the remainder of the course we'll move through, we'll be making an attempt to at the very least get through chapter 5, where we take all these idealized assumptions that were so great and see when they break down more back to the real world. If we have time, we'll pick up instrumentation amplifiers from chapter 6. Thanks, and see you for chapter 5.